Oh, okay. It's a great privilege to be here. Thank you very much, Professor. My name is Love Allen Chijoke Ahakonyi, Love for short. Feel free to call me Love, it's fine. I graduated from the IT Convergence Research, IT Convergence Engineering Department, and like Professor Elias said, my research area was in IoT reliability. I majorly focused on IoT reliability with more attention on anomaly detection. And I hope you will enjoy this class today. How many of us, it's going to be a very interactive class. Feel free to ask your questions, and I will be asking you questions. Please, I want us to engage. How many of us, you have an idea of what anomaly is, or anomaly detection? You have tried it, you've read about it, you have heard about it. I'd like to know what you heard about it, what you know about it. Anyone? Tell us. Very correct. Yeah, so I have the right audience. And I'm sure every one of us knows a thing or two about it. Thank you. And so today we are going to look at this area in this order. We'll look at the fundamental concepts and then the types of anomalies, the approaches that are already in use and future trends, and then the case study of SCADA systems, which we have extensively explored in our laboratory, and the challenges in anomaly detection. Even though we are trying to detect a rare event, there are still challenges. And then I want us to have an open mind. You can also get a direction for your research work as we discuss. And then we'll look at the summary and your questions. What's going on? Okay. I wouldn't mind knowing your names. I think that's Ranim, right? Ranim. Like Ranim said, it's about identifying rare scenarios, which is very correct. Now, anomaly. It's basically an abnormal situation in an environment that it's not expected to occur. And the detection is basically ability to identify these rare scenarios. For those of us in data science, deviations in data points, data patterns, observations that are significantly different from what is expected to be. And so also there can be intrusions. So sometimes there's this confusion about anomaly detection and intrusion detection. I will say today that intrusion falls under the category of an anomaly detection because anomaly may not be intrusion. It may, as we go on, we'll see the different classifications. Now, the core idea behind anomaly detection, like I outlined here, ranges from ability to stop or prevent an attack, if it is an attack, and then the readiness to maintain an operational system. You know, for instance, in an industry, we carry out anomaly detection to be able to maintain the operational system and enable it to continue without interruptions. And then the anomaly itself. What is that is out of the ordinary? And then the intrusion. Is there unauthorized access? Then identifying, being able to spot the difference, being able to spot the unauthorized access to the system. And when there is an identification, we come to the classification of the identification. What kind of identification, what kind of anomaly? Is it as a result of equipment malfunction? Is it unauthorized access? And what is the cause of the anomaly? That is where we get to the why. We have to find out what is responsible and provide a solution. Is it mitigation? Is it isolation? Whatever. And then for attacks, what do we do? Is it malicious? Is it benign? And that also determines what action should be taken. Now, anomaly detection can be used in credit cards. That's how fraudsters are detected in financial institutions, insurance companies, network security. We detect what deviation is in the network architecture. And then in our healthcare, anomaly detection is employed to also detect rare diseases, classification of cancerous malignancies, and all the rest. In the manufacturing industry, it's also used to detect faults and defects. For instance, in production, a production line, anomaly detection is also employed to detect defects in products and faults in equipment. And then it's also employed to enable predictive maintenance. If we're able to detect a possible anomaly in our operational equipment, it enables preparation for predictive maintenance. Then we come to the types of anomaly. We have the point anomaly. As we can see from the diagram here, the anomalous point here, we can see that it is a single point of deviation from the group classes. We have group classes, 2 group classes, and the point of anomaly is a deviation from the 2 classes, both in structure and in position. And then we have the contextual anomalies. For contextual anomalies, a typical example is a scenario like we are in this region. This is winter season. Imagine a scenario where someone has a temperature of 35 in winter season. It's an anomaly. Sometimes it calls for investigation because in summer, temperature of 35, it's fine. But in winter, there will be a need to investigate to find out why this high temperature in this period when we know temperature falls below negative. And then we have the collective anomalies. This is an example, is a sudden spike for network administrators who are constantly monitoring network operations. You suddenly observe a spike in the network traffic. The first point of call in mind is what's going on. Is that a distributed denial of service attack? What could be responsible for the sudden network traffic spike? So we call that a collective anomaly. And then various approaches have been in use. Anomaly detection has come to stay. It's been extensively explored, and exploration is ongoing because attack mechanisms are getting sophisticated and attack types are also getting sophisticated. So it is a continuous work that we as researchers will have to keep providing and profiling solutions that will continue to mitigate and apprehend such situations. Now, the first here, the image here is a typical flow is a basic flow of a typical anomaly detection. However, the approach differs when it comes to the middle box. Now, this is a statistical method. Anomaly detection can be statistically carried out for data points, to identify data points with low probability. If you are a statistician, you understand that in the probability distribution, there is a concept and there is a range. Now, if the values fall below the expected, it is an anomaly, and that can be done. I put a few examples here. We all know that there are more approaches to statistical methods. The next here is machine learning. We all know a lot about, I assume we all know a lot about machine learning. Anyone here who hasn't tried machine learning? Or you haven't heard anything about machine learning? So, anomaly detection is extensively done using machine learning. I had to categorize them because when we talk about machine learning, it's holistic. So in machine learning, we have the supervised learning. For the supervised learning, it requires a labeled data. And this labeled data has to include a normal and anomalous data distribution. So those are some examples of where's my pointer? Some of the algorithms, there are much more algorithms for supervised learning. So for the semi-supervised, for supervised learning, the data has to be relatively large. For semi-supervised, you can employ small data that is labeled to carry out a semi-supervised. Basically, the semi-supervised is used to improve unsupervised methods. We'll get to the unsupervised, where the semi-supervised, the model is trained on it trains the label data and employed for using the unsupervised methods. Now, for the unsupervised method, no label is required, and the unsupervised approach assumes that all data is normal. In this scenario, oftentimes we employ the clustering algorithms like we saw in the single point anomaly, where you cluster similar data and to be able to identify the anomalous point. And then we can also use isolation, what we call the isolation forest. The isolation forest enables you to identify the single point which is different from the normal event or the normal data point. And for the unsupervised learning, also require a large amount of data. But there's something I want to point out here. For machine learning approaches, the volume of data is very important because the anomaly detection in real scenarios is minimal. So we usually don't find large volume. Imagine a scenario where a financial institution reports about 90% of the credit cards are hacked. That is a stop show. I call that a stop show scenario. We know it's not possible. It is possible, but measures are in place to prevent that. So anomaly is usually rare. That is why in the data we have, available data we have what we call imbalanced class, where the normal scenario outweighs the anomaly. And then we have the proximity-based methods. The proximity-based method here identifies an anomaly based on distance or density, like we have here, and it employs the local outlier factor. As we can see in the diagram here, the distance or density is calculated based on the anomalous scenario. We can see this is a normal scenario, and the density is calculated for the anomalous points. And so we employ the k-nearest neighbor local outlier. Isolation forest also can be employed here. And then we have the clustering-based methods, like I mentioned earlier, where we tend to group the data distribution according to types, and that enables us identify the anomalous point in the distribution. As we can see in the diagram here, this is a normal distribution, data distribution of objects, and then the anomalous points are identified here. So clustering enables us to group the data according to types, and when the points outside the groups are considered anomaly, and then those points are further investigated and classified as benign or malicious, or what kind of anomaly it is. And then we have also deep learning approaches. This deep learning has also been extensively explored, like illegal traffic detection, like in healthcare, the retinal damage. This is mostly used by the optical healthcare facilities. And for the network scenarios, we use deep learning to identify the deviations in the image classes of data. Like deep learning mostly is used for vision-based data, even though it's also used for numerical data. But I consider that using a sledgehammer to kill an ant. And then we also have in the industrial IoT. Now, this is the focus for our class today. In our lab, we have extensively carried out work on anomaly detection based on SCADA. Someone may ask me, what is SCADA? Who knows what a SCADA is? SCADA. You've heard about SCADA? How come I'm the only one talking? Can someone tell me what a SCADA is? Amazing. Okay. SCADA is it's an acronym for Supervisory, Control, and Data Acquisition. It's a system software that I call the hub of the industry. It's used in monitoring industrial operations. And so the reason our focus is on SCADA is without SCADA, I would say there is no industrial operations. So that means the focus of intrusion will be at that system. So that is why we took our time to study the anomaly in SCADA systems, how to detect them, and how to prevent the intrusions. Now, the anomaly detection in SCADA is based on some factors like data quality issues that may develop from dropouts or packet loss, the latency of the system operations, repeated values, measurement bias, noise in the measurement systems, bad or missing timestamps, if you're familiar with SCADA. By the way, if you have any question after this class about SCADA, please feel free to reach out to me. I have a lot to explain about that if you feel lost here, but I don't think anyone should feel lost. I had to bring it as basic as possible to enable us flow along. Now, it's also possible due to loss of GPS, synchronization, incorrect signal metadata, poor server performance, improper device configurations, incorrect phase sequence, missing phase connections, and then cyber attack. You can see here that cyber attack is just one aspect of an anomaly that can occur in a system. So, looking at this flow here, this is a SCADA data quality. We can perform a conformance. For this sketch, I call this how we can detect anomaly in a SCADA. Okay, so we can do that based on conformance testing, the statistical and data mining approaches. The data mining includes machine learning, deep learning, and all others. And then we have a new focus. This is emerging, the physics-based bad data detection, and then in-lab testing, sometimes during experimentations, and we can also detect anomalies. And then remote testing after installation, equipment installation. Those in industrial scenarios will understand this. And then cleaning data streaming, cleaning archival data, hybrid or linear estate estimation, and substation level estimations. I'm sure this will make sense to those in grid and power grid and mechanical areas. Let's move further. Now, this is a SCADA. The SCADA system has a typical cyber physical systems. So someone may ask, I had to put this here to also help us to understand what the cyber physical systems, for those of us who are new. Basically, it's a combination of hardware and software systems like the sensors, actuators, and mechanical systems to control and monitor the physical system like we have here. This is the physical environment, and then this is a cyber environment. Now, we look at the flow, the arrows, the broken arrow is the information flow, the bold arrow is energy flow, and then the bounded area is the region of safety hazard. So we can see the points where a possible intrusion can come in. We call this saboteurs. It may be someone in the system. Oftentimes, it may be unintentional. Some actions that constitute anomaly may necessarily not be intentional. And then we have the natural environment surrounding people, which is within the physical interface. And we have the external access and physical processes. And then for the cyber environment, we also have the hackers. We all know that hackers intrude our systems from the cyber world. So, which is also possible through the human-machine interface, and then external operators. So you can see that points of intrusion can come from the physical environment or the cyber environment. For the physical environment, it could be from fellow operators, system operators, and from the cyber world, it could be malicious users. And then we have the external supervisory control. This is a combination of the hardware and software. Excuse me. It is important to know that these systems, industrial systems, or any system basically employed for operations is prone to cyber attacks, several cyber attacks. These are just a few, like man-in-the-middle attacks, distributed denial of service attacks. And then, so looking at this structure, critically, you can tell where the points of attacks can be. My pointer keeps going off and on. Where the points of attacks can be. And for a typical researcher, I think, like when I attend classes, based on my research area, I look out for where I can leverage on. As a researcher, the question to ask yourself is, where in this scenario can I situate my intrusion detection system? Should it be at the physical environment or the cyber environment or the cyber layer? Where? Or within the region of safety hazards? So constructively, you can decide to locate your intrusion detection system any part of the cyber-physical system of your choice. Because looking at this entire structure, it's all prone to intrusion. And so the goal is to protect this structure. And how do we protect it? By developing a system that should be able to monitor data flow or network flow, as the case may be, to be able to identify an anomaly. When an anomaly is identified, what's the next point of action? Classification of the anomaly and mitigation. So that's the reason I put this here. And now, like I said earlier, we have extensively carried out research in this aspect, like cybersecurity, anomaly detection, classification and characterization in SCADA systems. You can find these resources online. We have the institution has free access to all these papers, so you can find them. If you have any question on any, you can reach out to me. In this, we employed a tree-boost aggregation for dictating and characterizing IoT SCADA network traffic. Now, one may say, why IoT SCADA? A SCADA system has evolved over time. We have the first generation, second, the first generation stemming from the standalone, then we had the peer-to-peer, until we got to the IoT SCADA network systems. So we figured it's important to also consider the integration of IoT into SCADA systems, or rather SCADA into IoT systems. So how do we also protect this interconnectivity? So we had to look at the tree-based algorithms. We extensively worked on tree-based algorithms because we have also been able to ascertain that tree-based algorithms, based on our previous works, that tree-based algorithms have proven to be excellent for intrusion detection with minimal complexity and resource usage, because the tree algorithms, because our focus is on real-time operations. So if you're considering real-time operations, you should go for systems that are computationally less complex. Imagine you're trying to dictate an attack, and your model is taking like 10 minutes to do that. You can tell it is computationally inefficient because the attacker takes splits of seconds to get into your system. And so we had to come up with that. And then here, we also had what we call the agnostic. Agnostic in the sense that this is a combination of chi-square. The CH is basically an acronym for chi-square. Chi-square is a statistical approach of feature selection in combination with the decision tree algorithm. So we call this agnostic because you can substitute the chi-square for any feature engineering of your choice, a feature selection approach of your choice. So you can decide to put your PCA here. You can decide to combine a technique with your RFE. It still works. That's why we call this agnostic. Basically for high-dimensional data-aware systems, because with IoT, there is big data. When you have enormous data, and in that enormous data, the anomaly is minimal, almost inconsequential. What kind of model will be able to identify the insignificant anomalous scenario? So that's why we came up with this work. And here, a similar thing, but the difference here is that we had to work on encoded traffic. We know that we have different types of network traffic. And so the focus here was on encoded network traffic. And here we also looked at encoded network traffic in smart factory. And here, observe, I skipped out this, I'll come back to it. And then here we also looked at fusing this model. This was where we tested and came up with this one, the agnostic. And so here we also looked at software-defined IoT networks in a combination of LSTM and deep neural network. Whereas this was, here we looked at a combination of CNN and LSTM. And then for this, we also looked at when predictions are made, our model says, oh, this data is anomalous, or this is an attack. Why did the data make such decision? How can we be sure that what our model predicted is correct? And so we had to also look at the explainability of machine learning algorithms. Why do they make such decisions? And so we also came up with this work, and we have other works in progress on AI explainability. Now, what are the possible cyber events? Like I mentioned earlier, they can be bad data, denial of service, spoofing, as common as failure in communication line. It could be noise in the sensor, and then malicious attack, a packet loss, huge latency, false injection, and a man in the middle. As minimal as the jitter in our network traffic, it constitutes an anomaly. We need to check why the jitter, what's possible, what's the possibility of eliminating the jitter, what could be responsible for that. And this can also be analyzed using the log data files, the data traffic, and then the intrusion data, and then threat sharing. And for the intrusion data, these IDS, it's an acronym for intrusion detection systems. So when you develop your intrusion detection systems, you are going to be employing the data for intrusion detection. Now, having come this far, we also came up with certain difficulties and limitations of the anomaly detections, because in detecting an anomaly, a problem arises. How do we resolve that? What do we do? So I put here some of the challenges. Remember, I talked about data imbalance. And in data imbalance, it means, like I said earlier, that anomaly is rare in data distribution. So it makes it difficult to train our models. So for researchers, the goal is, what model do I develop to be able to take care of this scenario? A high dimensional heterogeneous data, a data distribution where various sensors are employed, temperature sensor, radiation sensor, water flow sensor, pressure sensor, and the data will not be the same. Some data will be images, some data will be time series with different ranges. So how do you manage the data and be able to still identify the anomaly? So also the case of false positives and negatives. In training intrusion detection models or anomaly detection approaches, it's important to be able to balance precision and recall. Oftentimes, I see some research papers, and authors are focused on accuracy. I personally don't look at accuracy. When I see the accuracy, wonderful. I go to look at the F-score. Now, what does that tell me? The F-score balances the precision and recall. Your F-score, the value of the F-score tells me what your model is truly like. Because you can, I encourage you to try it out. When you develop your models and you have a wonderful accuracy, look at the F-score. When I see a paper that F-score is missing, that's a red flag for me. I suspect the model, because you should be able to put all the features, your metrics there, to enable me see how your model performed. And then being able to define the normal behavior, because normal behavior changes over time. We'll call that concept drift. So how do we mitigate that? Do we develop a model that should be able to keep monitoring the scenario to be able to apprehend the concept drift and ascertain at what point there was a concept drift? Now, the interpretability. That was why I left out the last research work. This is very important because imagine you go to the hospital and the machine detects, oh, there is a benign growth or a malicious growth. How did the machine come to the conclusion? That's why it's important, because when there is the argument we have here as researchers is when AI tools are employed in certain areas, who will be responsible when there is a failure, when there is a wrong decision? Are you going to charge AI to court? If the answer is no, then what do? That is the reason for explainability. Because certain models are hard to interpret. That's, again, the second reason why we focused on developing the tree algorithm for our research works, because they are explainable. In tree algorithms, you can see why and how the algorithm arrived at the decision. And then, finally, the high dimensionality. Why do we have such dimensionality? Because it makes dictation difficult, and very, very difficult if you've worked on this area. And so these are possible researchable areas I encourage you to look at and see what you can do as researchers for any field of your choice. Now, let's look at the common causes of the challenges to the SCADA systems. It could be, I mentioned earlier, unintentional acts by employees as a result of human error. It could be natural disasters, equipment failures, insider attacks, and then equipment aging and failures, enemy nation attack, interoperability can also cause anomaly. Most developers of softwares and hardwares find it difficult to come to terms on the issue of interoperability because everyone wants to sell their product. So that's also a problem. Now, summarily, we have looked at anomaly detection, which is vital in identifying rare scenarios in various aspects of life. And we also looked at the techniques, which range from simple statistical approaches to our deep learning models. Now, I think I had a second PPT, I think that was not included, where I had put that current trend in detecting anomaly detection is actually focused on the integration of blockchain and quantum techniques with AI. And at the moment, we have lots of work ongoing in that area in the lab. And we have actually done a lot in integrating AI and blockchain, AI and quantum techniques. So we also looked at the challenges, which includes imbalanced data, concept drift, interoperability, and all the likes. And the practical applications span IoT, industrial IoT, finance, healthcare, and cybersecurity. I don't know what areas you are into. Anomaly is crucial. So based on that, I think I have come to the end of our discussion today. I would like to have your myriads of questions. I am here to give you answers.
Education by Korean also. Okay. I will translate for her.
Okay? Anomaly prevention, of course.
Because what I was thinking is about the anomaly detection, there should be some latency, right?
Yes.
Yeah. So yeah, that's my first question. And then the second is, how do you differentiate between the anomaly and noises or outliers? Because I think the noise or outliers, we just need to ignore it.
Sure. Okay, I'll take your question from the current. When that is the reason for anomaly detection, like we said earlier, anomaly is identifying a rare occurrence. When a rare occurrence is identified and we classify it, remember I talked about detection and classification. When we classify and it is noise, sensor noise, based on the system's operation, is it negligible? Then if it's negligible and the system requires ignoring it, of course you go ahead and ignore it. But when it poses a challenge, remember, in anomaly, I didn't go deeper because I needed to ensure that we are at the same level because we are all new. The system has a mitigation approach. As a developer, when you design a system for detecting anomaly, it doesn't just end with detecting. After detection, what next? So based on the mitigation approach, the next line of action, is it to mitigate? Is it to isolate? Based on the findings, the action is triggered, whether to ignore, mitigate, isolate, or even shut down. Then for your first question, you talked about anomaly prevention. Based on the cyber-physical structure I showed, now, that can also be leveraged to looking at the possible points of intrusion. Anomaly prevention technique can be developed, but because there is always intrusion, the focus is mainly on detection. But the detection can also be employed, integrated with a prevention mechanism, such that when there's a detection, and then the activation, the prevention is activated. Does that answer your question? Okay, thank you. Any other question? or suggestions based on what you're already doing, you think you need further clarification? Thank you very much, Professor.